Hello, how are you? Welcome to our today's lesson. Today we are going to look at this from one topic, particulate nature of matter. So we are going to start by looking at what matter is, and then from that particular point we'll be able to see the behavior of matter in different states. So when we talk about matter, matter is anything that occupies space and has mass. And I believe we have already looked at this from our science in primary schools, and coming into secondary school under physics, we are going to expound on this so that we can look at the three states of matter in details. Then we say these matter exists in three forms, and I believe we know those forms. We have the solid state, liquid state, and the gaseous state. Then we can talk about matter being which is not continuous, but it is made up of very tiny particles. Hence, the topic of the day, which is particulate nature of matter. Therefore, we can say that this particulate nature of matter refers to the existence of matter in very tiny particles. So we want to move to the first set of experiment to determine that indeed matter is made up of tiny particles. And our first set of experiment is by use of pieces of paper, or a small piece of paper, which we are going to subdivide continuously, and then we'll be able to see whether we'll have the last part or we'll get to the tiniest particle. So a piece of paper can be cut continuously until when the small pieces cannot be cut into pieces any further. This suggests that the sheet of paper is made of tiny pieces of paper. Hence, matter is made up of tiny particles. So as you can see the figure we have there, that piece of paper initially was big, then it has been divided into smaller pieces continuously to a point whereby we cannot cut the smallest piece into any other piece. That means that matter is made up of tiny particles. Then moving on, there is also another experiment which can be able to tell us about this. There is a concept of the matter is made up of tiny particles. So this is the diluting potassium permanganate solution, and in this case we are going to look at this process of diluting the purple potassium permanganate solute 7, and we can continue diluting this potassium permanganate until the solution appears colorless. This suggests that the particles of potassium permanganate are spread evenly in water, and each dilution process spreads them further. This is a proof that matter is made up of tiny particles which can be separated. So as we move on, we'll be able to see a video or to show this dilution process. Then we can have a question here that we explain why it is possible to dissolve sugar in water without any noticeable increase in volume of water. So as we are seeing is that the sugar is going to be broken down into the smallest particles. So our answer for that, we have that the sugar particles occupy the small intermolecular spaces of water molecules. This behavior of sugar suggests that matter is made up of very tiny particles. So the sugar particles can be broken down into very small particles, which can occupy the small intermolecular spaces in the water molecules. So that is a very good question, and I believe you've noted it somewhere. Then now, with me here is a video of the dilution process, and I want you to be very keen. We have the dark potassium permanganate. Then we subdivide a little bit of it into another glass. We add water. Then again, we are going to again subdivide a little bit of that potassium permanganate, and at the end of the day you can see on the screen there we have 4 glasses of potassium permanganate, and each glass has the solution which is of different color. The first one is dark, and as you are moving to the other side or to the right, you can see the dilution process has taken place. That is repeated dilution, meaning that the particles of potassium permanganate have been reduced completely as we move towards the right. That is the repeat dilution process. Then moving on, we can look at another concept which is Brownian motion. And this Brownian motion refers to the random movement of liquid and gas particles. Random movement of liquid and gas particles. So to demonstrate Brownian motion in liquids, first of all, we'll consider the setup alongside in which chalk dust is sprinkled on the surface of water in the beaker, and the beaker covered using a transparent lid. This behavior of chalk dust is then observed with the help of a hand lens, as we can see in the figure. So that is for liquids. Then we have this other one for gases, Brownian motion for gases, and we are going to consider the smoke cell experiment. And in the smoke cell experiment, you can be able to see that in the smoke cell experiment we have smoke trapped in a smoke cell, and then we have a transparent lid that is covering that smoke so that it cannot escape. Then from the right hand side we have the candle flame and we have the converging lens. Then we have microscope up there which will enable us to make the observation. Then there is the human eye whereby you'll be positioning yourself. So we should note that the smoke is introduced into the smoke cell by pouring the straw, by burning the straw and letting the smoke fill the smoke cell from the other end. Smoke is used here because smoke particles are light and bright. So we should note that reason why smoke particles are used. That is also commonly tested. Somebody can ask you to explain the reason why the following are used. One, they'll ask you to give the reason why smoke particles are used. So you can see they are light and bright. Then we can talk about the converging lens. What is the role of this converging lens? This converging lens is used to focus or concentrate or converge the light to the smoke cell, so thereby illuminating the smoke. So converging lens, its work is to focus or converge or concentrate the light to the smoke cell. Then we have the microscope. This will assist the observer to illuminate smoke particles clearly. So the smoke particles will be illuminated for easy visibility. So that one will help us. Then the bright specks are observed. So the observation, once you look through the microscope, what are you able to see? The observation is what somebody is able to see. So what is observed? We are able to observe that we have bright specks that are moving randomly in the smoke cell. So that is the observation. Then or we can also say we are able to observe bright specks in a continuous random motion, that is in the smoke cell. The bright specks can be explained. Why are we able to see the bright specks? So once we have already given the observation as bright specks being seen in a continuous random motion, then we can explain this observation. Why are we seeing bright specks? Why are they in continuous random motion? So the bright specks are the smoke particles which have been scattered or been illuminated by the light particles, which or the light shining on them, And then we can also explain the bit of the random motion. The smoke cells are in continuous random motion because they are colliding with the invisible air particles which are in the smoke cell. So from that particular point, we can be able to give a lot of details from the smoke cell experiment. So this one was supposed to be for the first one. We had talked about some chalk dust particles are given there. So we want to move straight to what we call just a little bit. There is a question which we can ask under the smoke cell. You know, these are the sensitive parts which we need to give a lot of attention to. Somebody can ask you to explain what happens when there is a temperature increase in the smoke cell. So definitely there will be able to see the speed, or the bright specks will be moving faster because of the increase in the kinetic energy of the smoke particles. So that is also another good question. So for students, you should be able to be prepared to answer questions from this part. Then now we want to look at the kinetic theory of matter. After looking at this behavior of particles which are from matter, then we can be able now to generalize and give the kinetic theory of matter. So from the above experiment on Brownian motion, it constitutes that a kinetic theory of matter, which will state that matter is made up of tiny particles which are in continuous random motion. So as a student, you should be able to state the kinetic theory of matter. You will say matter is made up of tiny particles which are in continuous random motion. Then there is now another critical part, which is the arrangement of particles in matter. The arrangement of particles in matter. We start with the solids. We have solids are closely packed together in an organized manner and in fixed positions. Particles in solids do not move randomly, but instead vibrate about their fixed positions. That is the vibratory motion because of very strong intermolecular force. Those are the strong cohesive forces holding together, or that force of attraction between molecules of the solid particles, that is cohesive force. This explains why solids have fixed volume and definite shape. Then moving to the next state of matter, we want to see its arrangement is the liquids. The liquids, the particles in liquids are not closely fixed as in solids, but move about randomly. That, as we have seen in the Brownian motion. This is because the intermolecular forces in liquids are weaker than those in solids. Then the same reason explains why liquids have no fixed shape. Explains why liquids have no fixed shape but assume the shape of the container. The intermolecular force in liquids is stronger than in gases. A reason as to why liquids have to have fixed volume but gases don't. Then we have the next bit, which is gases. For gases, um, particles in gases are farther apart and have an increased random motion compared to liquid particles. This is because of very weak intermolecular forces in gases particles as compared to liquids and solids. The same reason explains why gases have no definite shape and volume. So we have a very small video here to also help us see how the arrangement of particles is. So as you can see, that is a video to show a solid. There is a stone there. This is how the particles of the stone are packed closely together, very fixed. Then this is the second one, is a liquid, definitely water. You can see how those particles are not as closely fixed as those of the solid. Then we have the one for the liquid. So I can just repeat that video. Check those ones for gases. The last one, you can see that's a gas. They are scattered very far away from each other. Then there is another one here, still to emphasize the same on that arrangement. Look at the solid arrangement. Particles are closely packed together. Then the liquids, particles are not as close as these for solids, so you can check this. Then these are gases, and you can see if we hit, that is how they are going to vibrate. These are liquid, these are gases. Good. Then move to the next part, under which we are going to look at uh, change of state. And under this part, we have a question which somebody or students are supposed to explain, but I'm going to give an opportunity so that you can see some videos which are going to explain the change of state. Use a block diagram and correct terminologies to show how one state of matter changes to the other when the temperature is changed. Define all terminologies used. The first one, we are talking about melting, the process by which a solid changes to a liquid at a fixed temperature. Then we have evaporation, process by which a liquid changes to a gas at any temperature. We also have condensation, the process by which a gas changes to a liquid at fixed temperature. Then there is freezing, changes to a solid at fixed temperature. Then sublimation and the deposition. So let us check that video that we have. So we are talking about change of state due to heating. So you can have this video and check what is happening. The first one, you can see there are solids on that pan. Then we start heating. Can assume that it is ice. Check that heating process. Look at the changes that are happening. Look at these how the particles are breaking down. Look at now how they are being weakened. Slowly the ice is changing to liquid, sorry. You can see that it has become liquid. Now those are particles of the liquids, and you can see now how they are moving. They are not as closely fixed as those in solids. Then as the heating process takes place, you can now see they change from liquid to gas. You can see the vapor that is moving up, and you can see the temperature on this other side has moved to almost 100 there. Then now we expect now this process to take place, that is vaporization, from liquid to gas, vaporization. Then can have an extension of the same, that is change of state due to cooling. We have once we go the reverse, something else will take place. So let me pause at that point. So from the gas we have condensation taking place so that we can have the liquid. Then from liquid we have freezing taking place, or solidification, so that we can have that solid state. That agrees with what we had discussed earlier on about those terminologies that are used. So those are under change of state. Then now the next part, we want to look at something that we know, which is diffusion, and we want to discuss about this diffusion. And under this diffusion, first of all, we want to look at what diffusion is. Diffusion is a process by which particles spread from a region of high concentration to a region of low concentration, and it's noticeable. Diffusion takes place in liquids and gases due to their continuous random motion. Then I have a video here so that we can show us what really diffusion is, because we have said it's from a region of high concentration to a region of low concentration. Now with us here is a spray that is full of gas, and that is where we have high concentration. As you press there, you are releasing. The spray is moving. We are having that gas being spread all over from where it's highly concentrated to these other regions, the outside of the container where it has a low concentration. So this is a good visual to show us what indeed diffusion is. Then moving from that part, we can talk about demonstrating diffusion in liquids. So we first consider the setup below used to investigate diffusion in liquids. We have concentrated copper 2 sulfate, blue in color, which is carefully and slowly introduced into the beaker through a funnel to obtain two layers. So this is what we have: copper 2 solution here, then we have water. This is the beaker, and this is the funnel to start definitely. After some time, it is observed that the boundary between the two liquids disappears and a homogeneous pale blue mixture is obtained. This is because there is a greater rate of movement of water particles from the water layer to copper 2 sulfate layer. At the same time, there is greater movement of copper 2 sulfate particles from the copper 2 sulfate layer to the water layer. So we are having diffusion from the copper 2 sulfate solution side. It is diffusing to the water, and then water, which is highly concentrated up here, is diffusing to the copper 2 sulfate solution. So we are having a homogeneous pale blue mixture at the end of the day, because now they would have diffused into each other and we'll be having a uniform solution. If hot liquids are used, the formation of the mixture will be faster because the particles move faster due to increased kinetic energy. Remember, temperature increases the kinetic energy of particles. So we'll be having faster movement, hence having a faster formation of the mixture due to the increased kinetic energy. Then we also want to demonstrate diffusion in gases. And when we talk about diffusion in gases, we want to first of all start with considering bromine gas. Already we have looked at diffusion in liquids. Now we want to look at diffusion in gases, and we want to start with bromine gas. Under this, you can check one jar filled with the bromine gas, and then the other one has air particles. It's colorless. And at the middle of those two glass jars, we have a cardboard, which is a separation mark. So we can also now explain that and say when the cardboard is moved and the two jars pressed together, it is observed that homogeneous pale brown mixture forms in the two jars. And remember, bromine is a brown gas, but we are saying, but when they are pressed together, it is observed that homogeneous pale, remember the other one was brown, but now we're talking about pale brown mixture which forms in the two jars. This is because bromine gas spreads into the gas jar containing air at a greater rate. At the same time, air spreads into gas jar containing bromine at a greater rate. So the two gases are diffusing into the regions where they have a lower concentration. Air is moving into the bromine, and bromine is moving or diffusing into the part where we have air particles. So we can generally say diffusion in gases is faster than in liquids. First of all, because gases have a low density, then gases have a high kinetic energy, then gases have weak cohesive forces. The next part here, we can look at a small video here to show the same experiment that we have already discussed about bromine. Look at these two tubes or glass jars. One has bromine, this lower one, and the upper one has air. Once they are put, that cover is removed, you will see the two gases are mixing equal lower concentration of bromine. So initially bromine was brown, but as we are mixing, we are having a pale brown mixture that has been formed because of the diffusion of the two gases moving into the where they have lower concentration. So that one is done. Then what are the rates of diffusion of gases? So as we know, different gases have different rates of diffusion depending on their density or relative mass. So different gases diffuse differently because of their densities and their relative mass. A gas with a high density has heavier particles and therefore its rate of diffusion is lower than the gas with the lower density. So that one should be noted. For high density, it implies that the gas has heavier particles. Then with us here is a small video to show how ammonia gas and hydrochloric gas, their conch, how they are going to diffuse so that we see what will happen. So cotton wool is dipped in ammonia solution and is kept at one end of the tube. As you can see here, it's on this side. At the other end of the tube, we place cotton dipped in hydrochloric acid. The two vapors diffuse and they mix to form white ammonia, this one here. So as you can see, let me play that small video there. As you can see, the diffusion is taking place. It shows that the aqueous ammonia is less dense than the hydrochloric gas. Now we are having this traveling fast and covering a longer distance. So the white ammonium chloride or the white precipitate is formed closer to hydrochloric acid, and I think you can check it here at this point that you can see this cursor. That is where we are having the white ammonia. That's where the two gases meet, and I think can look at a question from that part. Look at the figure that we have there. We have cotton that will soaked in concentrated ammonium solution. We have a tight fitted cork here, cotton wool soaked in concentrated hydrochloric acid, then transparent long glass tube. Then we have an example, a question that is going to use that figure that we've seen up there. In the figure above, ammonia gas and hydrochloric acid gas diffuse and react. Part A. State and explain the observation made after some time. In the video you've seen a formation of a white deposit. There is a white deposit. So a white deposit is formed near the cotton wool soaked in conch hydrochloric acid. So under the explanation, then now we are going to explain why it's forming closer to hydrochloric acid. So we can say ammonia gas is less dense and has light particles. Thus, it will diffuse faster than the hydrochloric gas, which is dense. Then on the diagram, show the observation. So as you have seen on this diagram here, there is this deposit that is been put here. This is now the white deposit, ammonium chloride, which is close to hydrochloric acid because we've already noted that ammonium chloride, ammonia is less dense than hydrochloric acid. Then we have another part. If the experiment was performed at a higher temperature, will you expect it to take longer or shorter to form white deposit? We explain. So, as we said, an increase in temperature results to an increase in the kinetic energy of the particles. So the gases will have more kinetic energy, hence they will vibrate more. So what does this imply? This implies that as the temperature increases, the particles will move very fast because they would have had an increase in the kinetic energy. Therefore, they will take short time. Then this is because the increase in temperature increases the kinetic energy of the particles of the gases and hence increase the rate of diffusion of the gases. We have already explained that. So we want to stop at that point for today. Thank you for listening. That was all about particulate nature of matter. And if you have a question, kindly leave us your question in the comment section so that we can be able to answer it in our next meeting. Thank you. And I would wish to stop at that point.